Okay, so we're going to go ahead and continue on talking about the Earth in relationship to the Sun. Now we know that the Earth is 93 million miles away from the Sun, and it is the third planet from the Sun. Oftentimes the slogan, "My very educated mother just served us nachos," is a phrase that's used to help memorize the order in Earth in relationship to the other planets. So we have Mercury, Venus, Mars, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now, so the energy from the Sun is referred to as very hot energy in the form of short waves. Now, short waves, when we start talking about short and long waves, we will be introducing and discussing the electromagnetic spectrum. Now, anything in the form of short waves is going to be associated with very hot temperatures. So the energy from the Sun are short waves that we identify in the electromagnetic spectrum for radiant energy. Okay, so some key terms that we want to talk about. In talking about the Earth's orbit around the Sun, we know that it takes 365.24 days to make a full rotation. Those 0.24 days are associated with leap year. So remember, leap year happens every 4 years. So that's to make up for that 0.24 days. The Earth rotates on its axis, and it takes 24 hours for the Earth to complete a rotation. And that's going to give us our night and day as it relates to the proximity and orientation of the Sun. We use the terminology polarity when we refer to the Earth's axis always pointing in the same direction as it's as it's rotating and as it's in its revolution around the Sun. We use a term called plane of ecliptic, which is a flat plane on which the Earth travels on. And we'll see a diagram to help identify this definition. What I will show is I'll provide a link to an additional resource that helps in animations describe the Earth-Sun relationship. So I'll go ahead and make this visible as we move forward. Okay, so to introduce some additional concepts, we see the Earth in the center of our screen here, or sorry, see the Sun. And we see that the Earth is depicted right here, and we can see the elliptic plane of the Earth as it completes its revolution around the Sun. Now, one thing that you need to know is that the distance of this elliptic plane, it's not totally spherical. There are certain periods where the Earth is further from the Sun than in other locations during the revolution. And we identify these points as the perihelion and aphelion. So the perihelion takes place on January 3rd, and it's the point of Earth's orbit where the distance between the Sun is the least. So that's 147 million kilometers away from the Sun. Now, we also have the furthest distance from the Sun that takes place on July 3rd, and we refer to that as the aphelion. And it's the point of the Earth's orbit where the distance between the Earth and the Sun is the greatest. Okay, so we don't have equal distance when we are, completing this orbital process. We do have an exaggeration where the Earth is at its furthest point and then at its closest point. So in looking at the terms that we just identified, we have a revolution around the Sun, and then we also have the Earth's rotation around on its axes. So direct rotation of the Earth is going to be counterclockwise. We also have the same counterclockwise of the Moon on its own direction of rotation. Now, in looking at the plane of elliptic, this is the plane in which the Earth, it's kind of an arbitrary plane in which it's staying on that plane as it is completing its revolution around the Sun. We also have the plane of equator. The plane of equator and the plane of elliptic, we see that we have a 23.5 degrees distance, which is also going to coincide with our axial tilt. So the Earth is not completely at a 90-degree rotation. It's actually tilted 23.5 degrees. And this number is going to become very, very important when we start talking about the Earth-Sun relationship and incoming solar radiation. So it's important to know that the plane of elliptic is the surface include all points on Earth's path around the Sun. and that the Earth's equator is at a 23.5 degrees tilt from this plane of ecliptic. And so that's just important to note as we're moving forward. And here's another example showing the plane of ecliptic and the path of the Earth's orbit. And we have this perpendicular to the plane of ecliptic, and we see that now as a result we have a 23.5 degrees tilt. Now this tilt fluctuates over 41,000 years, and this tilt can kind of fluctuate between 22.1 degrees and 24.5 degrees. So it definitely tilts back and forth. It takes a long period of time in order to change, but what the current tilt is at today is 23.5 degrees. So now this diagram makes a little bit more sense. We see that the Earth is tilted 23.5 degrees. Now, what I do want to point out is notice that the 23.5 degrees value here for the subtropics and 23.5 degrees in the northern hemisphere and southern hemisphere are starting to come into play. And this is where we have the majority of the Earth's intensity, the sunlight, hitting this area of latitude. So in our tropics and subtropics, and we'll talk about this in the following slides. Okay, so some key terms that you're going to want to identify and understand is the term subsolar point. And this is where the sun's angle is 90 degrees at any point in time. Okay. The sun angle is the angle at which the sun strikes the Earth's surface. We have our circle of illumination, and the circle of illumination is the dividing line between night and day. So half of the Earth is going to be receiving light, half the Earth is going to be receiving day. But we know that we have the fluctuation and distribution of energy that's going to be different due to the curved shape of the Earth. So as a result, we have different intensity of solar radiation that is experienced. Okay, so here this diagram is looking at the subsolar point. So we see that the subsolar point is hitting the equator at 90 degrees. And everyone see that here? We have a nice 90-degree angle that's identified here. And so that would be the subsolar point. Anything that is not 90 degrees is going to be referred to as the sun's angles. So we see that up in the northern hemisphere at 40 degrees of latitude, we have the sun's angle hitting the Earth. I'm sorry, that's at 50 degrees in the northern hemisphere at a 40 degree sun angle. We also have, if we go down and look at 30 degrees south in the southern hemisphere, we see that the solar energy is hitting the Earth at a 60 degree angle. And we also identify the circle of illumination. So notice on the left-hand side of your screen, we have the night, and the right-hand side, we have day. So other terms that we want to identify is the angle of incidence, and this is the angle at which the sun's rays strikes the Earth's surface, okay? And also solar insolation. So solar insolation refers to the incoming solar radiation from the sun, and it's a common way to describe the energy that's striking the Earth's surface, and the unit of measurement is watts per square meter. And we'll be coming back to solar insolation in just a little bit. But to help provide a better example of the intensity of solar radiation when it's striking the Earth at 90 degrees versus at a lesser angle, we'll use the lamp example to help solidify this idea. Now, we've all seen this before, especially with flashlights, is that when the light strikes an area, such as a surface, at a vertical angle, we have a small area of illumination, but it's very intense. Okay, so we see that here on the image on our left. We have the light that's straight up and down, and it's striking a surface, in this case our desk, and we see a small area of illumination, but the light is intense. We can see more. Now, as opposed to taking the flashlight or the lamp and moving the lamp at an angle. So notice that we have a larger area of illumination on the surface, but it's not as intense. Now, the same idea and concept can be applied to the solar insolation striking the Earth at a subsolar point. So subsolar point would be the example that we're seeing on the left here, where the light strikes vertically and we have the most intensity of the surface, and that would be a 90-degree angle, as opposed to latitudes above 23.5 degrees in the northern hemisphere and southern hemisphere, where the light strikes the earth at an angle, not 90 degrees, so it's going to be less than 90 degrees. It's going to have a larger area of illumination, but less intensity. And so we can go ahead and apply that concept to this diagram here. So let's go ahead and look at the incoming solar radiation at the equator. So that would be this area right here. Notice that the area of light is going to be much smaller, more focused, versus incoming solar radiation at higher latitudes. So notice that at the 90-degree angles along the equator, it's a smaller area with more intensity. But if we move up higher in latitudes, we have a more area, but less intensity. And we can see that here with this angle showing that it's smaller than 90 degrees, but it's covering over a large area with less of that energy associated with it. So this is going to be a huge concept when we start talking about global circulation and energy. We know that higher amounts of energy is coming at the equator in the range of 23.5 degrees north to 23.5 degrees south. So that's going to be the area of our subsolar point, 90 degrees. Anything beyond that, above that, is going to be at a lesser angle. And so here's another example of looking at the distribution of our insolation, our energy from the sun, and where is the subsolar point 90 degrees? So see that it's identified on the image that the subsolar point where the solar insolation is 90 degrees, the most intense, is at 10 degrees south. We see that red line on our chart. Now anything above or below 10 degrees south is going to have a lesser sun angle and have a lesser degree of solar insolation associated with that surface. Now we can go ahead and start talking about the range of the subsolar point. Okay, so the range of the subsolar point, that means that between 23.5 degrees north and 23.5 degrees south, the solar insolation, the subsolar point, can be 90 degrees. And that's the range. It can't go above 23.5 degrees north or below 23.5 degrees south. And it just so happens that those particular lines of latitude are associated with our Tropic of Cancer, located at 23.5 degrees north, and our Tropic of Capricorn, located at 23.5 degrees south. And another date that should be popping up in your minds is June 21st and December 21st. So June 21st in the Northern Hemisphere, we identify this as the June solstice. And the June solstice is the longest day of the year, meaning that we have the most light. So that means that the sun, the subsolar point where the sun's energy, solar insolation, is striking the earth at a 90-degree angle, is at its highest extent at June 21st at 23.5 degrees north. Okay, so now let's go ahead into the southern hemisphere. Now, December 21st, we identify that as the December solstice, and that, for us in the northern hemisphere, is the shortest day of the year because the subsolar point is striking 23.5 degrees south at 90 degrees in the southern hemisphere. So there's more intensity and focus in the southern hemisphere than there is in the northern hemisphere. And so this range of the subsolar point is going to give us our seasonal shifts in solar insolation. Now, one take-home message here is just make sure that you understand the concept of a subsolar point, in that it's the angle in which the suns are striking the Earth's surface at 90 degrees. Okay, and we know that the range of the subsolar point here is going to be 23.5 degrees north and 23.5 degrees south. Anything above that latitude is going to have a less angle, lesser than 90 degrees, and therefore less intense of radiation, of solar insolation. Okay, so the next half of this lecture, we're going to talk about seasons and talk more specific about the Earth-Sun relationship.